So we have begun by talking about general equilibrium, and this was the background to the course so that you're all familiar, those of you who haven't taken freshman economics or intermediate economics, what's the background that's required for the course. And the fact that general equilibrium is a part of finance is, as I say, a bit of an innovation because most finance courses are taught entirely independently of economic theory. But the two greatest Yale economists and two greatest Yale financial economists had finance and economics integrated. And I believe that's the only right way of looking at the problem. And as I said at the very beginning, I think the events of the last few years have confirmed that view. So let's take up the question today of why is the free market supposedly so good. So we worked out two examples last time. The first example was, and the two examples are very similar to the first problem set that you did. In the first example, you've got two agents, A and B, and whenever we write agents A and B, we really mean a million agents just like A and a million agents just like B. The heart of perfect competition in the economy is that there's lots of people, and so we can't. Yeah, I think. All right, from now on, hand them in at the end of class. So we mean a million people of type A and a million people of type B. So the utility function of A, the welfare function of A is written there, and the welfare function of B is written, and they each begin with endowments. So when these 2 million people come together, they're going to be doing the same thing that you saw in the class on the first day. They're going to be haggling and arguing, and the buyers are going to always say the stuff's not worth very much, and why should they pay so much? And the sellers are going to say it's worth a tremendous amount, and they should pay even more. And eventually they're going to come to prices. And we discovered last time that the way of describing what prices and what final allocations they come to is by writing down a system of equations. And you did that all in your homework, and we came up with this outcome. So similarly, we did another problem in the last class, and we wrote down different welfare functions or utility functions and different endowments, and again we got the equilibrium. So we said that one of the amazing things is that these system of equations, the 6 equations for each economy that you solved in class, always have a solution. So the people who discovered that discovered it at the Coles Foundation. There were Ken Arrow, Gerard DeBrew, who was a Yale assistant professor, Ken Arrow, who was visiting the Coles Foundation in Chicago, but was a Stanford professor, and Lionel McKenzie, who actually taught at Rochester. The economic equations always have a solution. So what's so good about that economic solution? Adam Smith talked about the invisible hand, but you know there was no mathematics in Adam Smith. So why do we think equilibrium is such a good thing? After all, you saw in the example that there were 3 pairs of people who forlornly couldn't trade at all. So clearly not everybody gets to trade. Discrimination happens. Some people get the stuff, other people don't get the stuff. Well, the first approach of economists was that equilibrium maximizes the sum of utilities. So let's see how that works in this example. So this example is very special because everybody thinks that the good y has constant margin utility of 1. So that's going to play a big role in our optimization in maximizing the sum of utilities. So if you want to maximize the sum of utilities, you have to maximize 100 xa minus 1/2 xa squared plus 30 xb minus 1/2 xb squared, okay, plus, let's put it at the end, ya plus yb, okay, such that xa plus xb equals 84, which is the sum of 4 and 80, and ya plus yb equals 6,000. So the claim is that if all these 2 million people meet in their meet in a room like this and start shouting at each other and trading and offering deals and stuff. It's going to come down to a final allocation, which we've written over there, where A gets 77 of the first good and B gets 7 of the first good. And that final allocation is going to maximize the sum of utilities. So why should that be the case? In fact, in this example, it is the case. Well, why is it the case? Because there's constant margin utility of Y. So we don't have to worry about the Y allocation at all. Because if you increase YA and decrease YB, they still have to add up to 6,000. You're going to be lowering A's utility and raising B's utility by the same amount. So you won't have changed the sum of utilities. So the Y's are totally irrelevant to this maximizing the sum of utilities. So all we have to do is make sure that the X allocation maximizes the sum of utilities for the good X. So that, you can see, must be the case because we have to maximize the sum of two people's utilities, or 2 million utilities. You can always plug in XB is a function of XA, namely 84. So let's write it as a function of XA. Okay, and we can replace this maximization by recognizing that XB is just a function of XA. Okay, in fact, it's a very special function where the derivative of XB with respect to XA, so let's call the function, we'll call it that to denote that it's a function, happens to equal -1. Okay, so we want to maximize this over XA, taking into account that XB is just a function of XA, because if to maximize, you have to keep feasible. So we've now ignored all the constraints. Constraints have now disappeared, provided we keep track of the fact that XB is a function of XA. Okay, so why is it the case that the equilibrium 77 and 7 maximizes this? Well, the key is diminishing margin utility. We know that the utility function for, here's X, the utility function for A, is quadratic, so it looks something like that. Okay, and the utility function for B also looks something like that. And so if you look at this function entirely as a function of A, it's also going to look like that. Okay, so by diminishing margin utility, the function, the sum of utilities is concave. Concave, remember, is a picture like that. So what is the essence of a picture like that? It means that setting derivative equal to 0 is equivalent to, implies you are at max. So that's not true of any function. If you have a function like that and then it goes up like that, you could have the derivative of 0 here and not really be at the max. But because there's diminishing margin utility, more and more of X does less and less good, so it turns down. So all you have to do is figure out that the derivative is 0, which it is at this point, and then you're at the maximum. But that, at XA equals 77, has to be the case, because if you plug in XA equals 77 and you take the derivative of all this with respect to XA, of this whole thing, taking into account, as before, that XB is a function of XA, you just get 100 minus XA plus, okay, now it's just going to be 30 minus XB times the derivative of XB with respect to XA. Why is that? Because the chain rule. If I differentiate everything with respect to XA, and XB is a function of XA, it's just 30, because I'm taking the derivative with respect to XB, so it's 30 times the derivative of XB with respect to XA. Okay, minus the derivative with respect to XB is XB times the derivative of XB with respect to XA. So it's that. But if you plug in XA equals 77 and XB equals 7, DXB dXA is -1, you just get 23 minus 23 equals 0. because the margin utility of A is equal to the margin utility of B at equilibrium, the sum of utilities is maximized. And that's the end of the story. So that you noticed in the problem set, something like that. You may not have given exactly this argument. That was what you're supposed to have sort of discovered in doing the problem set, and now we've confirmed what you already pretty much knew. So are there any questions about that? Okay, it's just the simple generalization of our football ticket example, where the football tickets end up in the hands of the people who want them the most. And A happens to like a lot of tickets, not just one. And so A is going to keep buying tickets until he's bought 77 of them. And by then, the next football ticket's worth less than 23 to him. B, she likes football tickets a little less. She's not going to buy as many. By the time she gets down to 7 football tickets, she's going to think, so she hasn't bought nearly as many. When she's gotten to 7 football tickets, she's going to think the next one's worth less than 23. And since the price is 23, they're going to both stop there. So they're each going to stop at the same point where the last ticket is worth the same to each of them, and all the previous football tickets each bought is worth more to each of them. So there's no way of rearranging the tickets, because if you did, you'd have to take a football ticket that was worth more than 23 from one of them and give that ticket to the other one, who by then would think it was worth less than 23. So that's the argument. Okay, so economists were beside themselves with their brilliance in having proved this theorem and given a mathematical form to the invisible hand. Whenever you take a verbal argument like Adam Smith and turn it into a mathematical argument, you've understood it better. You understand why it's true, and you also start to understand why in some circumstances it might not be true. So for 50 years, let's say between 30 and 50 years, this was the fundamental argument of economics and economic equilibrium, that equilibrium was a good thing because it maximized the sum of utilities. But then little by little, starting with Irving Fisher and a bunch of people at the same time and a little bit later, so Hicks and Samuelson are famous for this, they began to wonder, what kind of crazy utility functions are these where there's some mysterious good that has constant margin utility of 1? So in modern terms, how could you justify it? You could say, well, maybe there's a machine where we can calibrate exactly how happy people are, and we can measure it. So, for example, we can measure how aroused their skin is. The skin texture changes as you become less and more aroused. Maybe we can measure that. With MRIs, we can measure brain waves. Maybe you can calibrate how many brain waves are spinning around and how happy somebody is. And maybe there's some mysterious good, like food, that has constant margin utility. Well, that doesn't seem very persuasive to me, and it wasn't to the economists of the beginning of the 20th century. They all argued, starting with Irving Fisher, that it made no sense to think that we could actually measure utility, and more than that, made even less sense that be some good that had constant margin utility of 1. So Fisher put everything on a symmetric footing and said, let's think of the two goods, X and Y, as more or less symmetric. I mean, there's no reason why one has to have some special role. So let's look at this equilibrium, which we got the same way, and you did this on a problem set solving for equilibrium. Does this maximize the sum of utilities? Well, the answer is, if it did maximize the sum of utilities, at the final allocation, we couldn't gain anything by switching, reducing 9/5 a little bit and increasing 6/5 a little bit. But what is the sum of utilities? Okay, so if you write WA plus WB, okay, it's going to be, for one thing, 3/4 log XA plus 2/3 log XB. So let's look at the margin utility to XA of good A. That's 3/4. So margin utility of AX plus margin utility of BX equals 3/4 times 1/9/5, which is 5/9. Okay, that equals 15/36, which is 5/18, if I've done that right. Doesn't sound right. 5/12, thank you. That sounds better. And now, but let's look at, so this is the margin utility of XA, okay, is 5/12. What's the marginal utility to B of x? Well, it equals 2/3 times 1/6, which is 5/6, okay, which is 10/18, which is 5/9. So these two numbers are different. The marginal utility to B is bigger than the marginal utility of x, is bigger than the marginal utility to A of x. So clearly, the final equilibrium allocation doesn't maximize the sum of utilities. By switching some goods from A to B, you could make both people better off. So that was a shock to economists. It meant that the argument they'd relied on, the thing which they were using to persuade, policy people that the free markets were a good thing, is a false argument. It rests on a premise that's indefensible, namely that there's constant marginal utility and everybody can measure it. So they needed some other definition of, some other way of capturing the mathematical idea that the invisible hand is a good thing. And the reason I'm spending so much time emphasizing this, even though you've seen this before, is because if economists made a mistake once, what makes you think they haven't made another mistake? So now let's give the argument that, in a weaker sense, the invisible hand holds, that is, that the free market comes to a very socially desirable equilibrium. And later in the course, we're going to find that that argument is also too narrow. So my point that I'm going to gradually get to is that economists have constantly taken too narrow and too special a view of the world. And as you enlarge the view of the world you have, not by making things mathematically simpler, actually you have to make them mathematically slightly more complicated. As you enlarge the view of the world you have, you get closer to the truth, and you start to find that the free market isn't quite as wonderful as you thought at first, and therefore there's room for government regulation. So it's not, as Paul Krugman argued, that economists are transfixed by mathematics and seduced into simple conclusions that the free market is perfect. On the contrary, I would say they were afraid of too much mathematics, and by looking too narrowly, they didn't realize what they could have just by being mathematically more sophisticated. So it's a failure of sophistication, not too much sophistication. So what did the economists argue? So the chief among them, Hicks, Samuelson, Pareto, and Fisher, all these people basically came to the same conclusion. They said, well, it makes no sense to talk about the sum of utilities. Let's talk about Pareto efficiency. So an allocation, so we begin, so what's the general problem? The general problem is you start with an economy, okay, made up of all these individuals. Let's call them WA and WB. But it could be as many as we want, so let's just say WI and EI. So EI is the endowment of X and EI of Y. So that's the economy. And now you start from the economy and you go to equilibrium. And equilibrium is a price vector, PX, PY, and allocations, X, I, Y, I in I, such that summation for all the i's of Xi equals the summation for all the i's of EIX. Okay, so everyone's I's final consumption of X plus J's final consumption of X plus everybody else's final consumption of X, those are the sum of the Xi's, is equal to the sum of everybody's endowment. And similarly for the Y's, all right, with EIY, and such that everybody is doing what's in their personal interest, which is maximizing WI of XY. So the max of WI of XI such that PX times X plus PY times Y equals PX times EIX plus PY times EIY is solved by XIYI. For all I. Okay, that's the definition of equilibrium. Everybody individually optimizes, looking at his own budget set, the hell with everybody else, does the best in his interest, chooses xi, yi at the going prices, supply equals demand. That's how you get the final allocation. So that's the definition of equilibrium. And now we're trying to argue that's a good thing. Okay, and so what's our criterion? Well, what Pareto and Edgeworth and everybody else decided is let's look at the welfare functions, WA and WB. So if you take some allocation, like the original allocation, 2, 1 and 1, 2, you'll have a utility, a welfare of each person. 3/4 log 2 plus 1/4 log 1. That's the welfare of A, and the welfare of B will be 2/3 log 1 plus 1/3 log 2. So that'll be some point here. So this is welfare B, welfare A at initial endowment. Initial endowment. But then if you look at the welfare at the final allocation, so 3/4 log 9/5 plus 1/4 log 3/2, you know it's going to be something like this. It's got to be up here. So it's going to be better for both people. How do you know that? Because A had the choice of just buying his initial endowment. That's always affordable, and he chose not to do it. He chose to do something else, and he was better off, and the same with B. So clearly the equilibrium allocation is going to be better than the initial endowment. And so the Pareto criterion is that an allocation x hat I, y hat I, Pareto dominates an allocation, so this is for all I, xi, let's put the i's on the top, if and only if everybody's better off. Wi x hat I, y hat I is bigger than Wi xi, yi. So we started with an allocation, the E allocation here, and then we moved to competitive equilibrium here, and everybody was better off. So the equilibrium allocation, Pareto dominates the initial allocation. But now the question is, maybe there's some other allocation besides the competitive equilibrium allocation that dominates the equilibrium allocation. So the theorem is that if P xi, yi, I and I is an equilibrium for the economy E. Remember, we defined the economy E. I'm going to put E here. Then no allocation x hat I, y hat I and I, Pareto dominates xi, yi if summation xi hat equals summation EIX and summation, got a little too tight here, sorry about this, y hat I equals, this is over I, equals summation EIY. Okay, so this is, yeah, I can read this, it's really bad, it's a critical line right in the corner. So I'll just say it in words and then read it literally. So this allocation dominates this one. The competitive equilibrium dominated the initial endowment. But maybe there's some other way of rearranging the goods that gets you even further out here. So the theorem says that's impossible. So it says if you start with a competitive equilibrium with an allocation xi, yi for the economy E, then no allocation, like that one, no allocation xi hat, yi hat Can Pareto dominate it? This couldn't happen. You'd have to be down here somewhere. That couldn't happen provided this other allocation used up the resources that were available. So the sum of the x's in this allocation is the sum of the initial endowments, and the sum of the y's in this allocation is the sum of the initial endowments over the people. So nothing else. Of course, if you add more goods to the economy, you can make everybody better off. But using the existing goods in the economy, which is the sum of the EIX's and the sum of the EIY's, there's no way to make everyone better off than at the competitive equilibrium. So it says literally if P, Xi, Yi is an equilibrium for the economy E, which is that, which includes the initial endowments, then no allocation Xi hat, Yi hat, Pareto dominates Xi, Yi if the sum over I of X hat I equals the sum over I of EIX, and if the sum of the Yi's over I, Y hat I's over I equals the sum of the EIY's. Okay, and now that's the theorem. So we've totally weakened the definition of equilibrium. So it might be that if this is the competitive allocation, if you look at this line, this is same sum of utilities. Right? Because if this slope is -1, and here's the utility to B and the utility to A, everything on this line has the same utility. So that theorem would say anything else that's feasible had to be down here. The sum is less than that. But here, we're not saying that. We're no longer saying that. Maybe you can increase the sum. From this equilibrium, you could increase the sum by taking something away from A and giving it to B. You could increase the sum. Okay, so that would have been here. You increase the sum. So you no longer have maximized the sum, but the fact is, to make B better off, you had to make A worse off. And that's the new criterion, Pareto efficiency. Okay, so that's the theorem, and now we're going to prove it so that you can see the whole logic of the free market just amounts to that. So are there any questions about this? You all supposedly saw this before, but that doesn't mean you really did. So does anyone have a question? What's going on? This is a very basic and incredibly important idea. All right, so give you one more chance. Somebody must have a question. Yes?
Could you just restate the theorem a little bit more slowly?
Yes. Why don't I draw a picture, which is what I was going to do anyway. So let's draw a picture. And I'll bring the theorem back after having drawn the picture. Okay, so the picture is going to be due to Edgeworth. So he invented the indifference curve, and he invented it in order to draw this picture. It was an incredibly clever picture. So he says, let's look at this economy, the one on the right that we start with. We put XA here and XB here. And you notice that A begins with an endowment of 2-1. So let's put his endowment 2-1 here. So this is EAX equal 2, and this is EAY equal 1. Right? That makes sense. Okay, now we can draw his indifference curves through that. So in his difference curves, he likes X more than he likes Y. So the difference curves are going to be sort of vertical. Right? He doesn't like to give up X very much. So his indifference curves are going to look sort of like this. And the most important indifference curves are the ones where he gets better off than he was before. So now in the end, there's going to be some price. There's going to be a budget set, which is X is way more expensive than Y. So there's going to be a budget set that looked like this. That's sort of the budget set that he faces. Right? And he's not going to choose this. It turns out he chooses something like here, which is he chooses a little bit less of X, 9/5, okay, and a little bit more of Y. So here's XA equals 9/5, which is a little less than 2, and XB he chose was, I can't read it, 3/2, which is more than 1. Okay, are you with me? You asked the question, does this picture make sense? Okay, so he obviously did better than he did before. But it's really much, you know, we got another guy to worry about. So how can you put the second guy in the same diagram? Well, let's just add the total endowment. Where's the total endowment? Well, it's 3 units of each. So here we've got 2. So this is 1, 2. This must be 3. Okay, so total endowment of good X is 3. 2 plus 1 is 3. And of good Y is 3 as well. Here's 1. Here's 2. Here's 3. This is supposed to be a square. So here's the aggregate endowment is here. This is the total endowment. 3 of each. Okay, but now we can put B. All right, so what is feasible? What are the feasible allocations? So this is an extremely clever insight of Edgeworth. He said, look, the total endowment is 3, 3. If I tell you that A has got 2, 1, that's this point, what's left over B must be consuming. So B is consuming the distance from here to here, which is obviously 1, 2. And if A ends up over here at 9/5, 3/2, okay, that's from here to here is 9/5 and 3/2. Since the total is 3, 3, B is obviously consuming what's left over. So he's consuming this difference. Okay, so whatever A does, you can see in the diagram looking at it the normal way. But if you just sort of twist your mind a little bit and look from this direction, once you know what A is doing, you can figure out what B is doing. So each of these points defines a feasible allocation. Okay, and now what we want to say, the theorem says, look at the utilities that A and B got out of this allocation. A is on this indifference curve. You know what he's doing, because B, you know, is coming from here. We know how he's doing. So look at the allocation they got. You can't make both people better off than that by choosing some other point in this square. So let's look at it from B's point of view. From B's point of view, B likes more of everything. So if A gets less, B's going to get more. So from B's point of view, the further out you go this way, the better it is for B. So the axis for B looks like that. So he's going to have some indifference curve that B's indifference curve is going to look B's indifference curve has to look like this. So here's where B started, here, and then B is going to be better off doing like this. So B's indifference curve looks something like that. Those are B's indifference curves. Okay, so the further out you go this way, the better off B is. So as you shrink what A gets, that obviously means B is getting more, and so B is getting happier and happier. Okay, so what is the definition of Pareto efficiency? Whatever point we pick, like this one to begin with, is there a way of making both people better off? Well, the answer is the competitive equilibrium makes both people better off. Why is that? If you can see it from back there. The reason is that A went from this white indifference curve to a better indifference curve over here. B, whose budget line is the same budget line looked at from his point of view, he went from his indifference curve over here to one here. Okay, so he went from this yellow indifference curve to a better one. So both of them got better off going to this final allocation than they started with. And of course that had to be true because A could always have chosen to stay where he was at 2-1. He moved to 9/5, 3/2 because it was better. And B could have stayed where she was at 1-2. She chose to go to 6/5, 3/2 because it made her better off. So both of them must be better off at the final allocation than they were to begin with. Okay, now what does the theorem say? The theorem says, remember in pictures, it says whatever point we pick here, that defines something for A and defines something for B. Then we can look at the utility welfare functions of both and see what indifference curves they're on. The theorem says there's no other point in this whole diagram which puts both A and B on a higher indifference curve for each of them than they were at the competitive equilibrium. So if I read the definition again, it says if I start with an economy there with the endowments and the utility functions, so the endowments and the indifference curves, and I compute the competitive equilibrium like we did over there, okay, then no allocation, that means no point in that box, could make everybody better off than they were at the competitive equilibrium, provided that new point is in the box. So it makes the sum of the x's equal to the sum of the endowments, and the sum of the y's equal to the sum of the endowments of y. Okay? So, Edgeworth, this is the end of the proof. We already gave the proof according to Edgeworth. Okay, so what's the proof according to Edgeworth? He says it's all a matter of looking at it the right way. It's easy to look at the picture from A's point of view. You just look at the x-axis and the y-axis. Okay, this is the y-axis. What is this? This is x, a, y was 3/2. Okay, so you look at, so this is the y-axis going this way, this is the y-axis, and this is the x-axis going this way. For A, it's very simple to look at the y-axis and the x-axis for A. A's got his indifference curve getting better and better, okay, and B, okay, so from A's point of view, it's very simple. You look at the endowment, you draw the budget line through it, which is some linear line, and then A picks the best point on that budget set, drawing the tangent, which is the white indifference curve to this point, right here. That's the best he can do. Now, the trick is to see that from B's point of view up here, things look very similar, because B's endowment is also at this point. He's got 1 unit up here of x and 2 units of y. Okay, why does he have that? Because the two together added up to 3. So if this is what A's endowment was, then of course what's left over is B's endowment. So B has to go here. Now, what does the budget set look like for B? Well, it's also a linear thing with the same slope, and it goes through this point. So from his point of view, this pink line is also his budget set. It goes from here all the way down to where it hits his y-axis down here. They've got the same budget set, just looked at from opposite sides. Okay, and now what does competitive equilibrium and supply equals demand mean? It means that when A chooses this point as the best point, okay, which happened to have been 9/5, 3/2, then B is happy to choose what's left over as his best point. So his optimal point, his indifference curve that's tangent to his budget set, has to be the same point looked at from his origin instead of A's origin. That's the trick. And so now you realize, okay, so that's the key insight that Edgeworth had, his beautiful picture. And now the point is that if the white indifference curve looks like that, anything that makes A better off has to be on this side of the white indifference curve. And the yellow indifference curve, which is B's indifference curve, anything that makes her better off has to be on this side of the yellow curve. But the white curve goes that way, and the yellow curve goes that way. So there's no point that's simultaneously above A's indifference curve and also above B's indifference curve. So therefore, nothing could Pareto dominate it. So that's the Edgeworth proof. Yes?
Well, no matter what, our point's going to be on our pink budget line. Because that's,
right.
That describes the endowments. That's all the goods we have.
The pink budget line describes what you can afford to buy, describes the budget equation, this equation. So everyone's going to choose on the pink line. Okay, now what's feasible is they could choose any points. It's feasible. This point is feasible. B gets almost nothing and A gets almost everything. B's never going to let himself be forced down there because B can choose something on the pink line, so he's always going to choose something better than that. Okay, so that's proof number 1. I'm just going to give proof number 2. So, okay, most of you have seen this before, but I'm going to give another proof, and then I'm going to ask you, then I'm going to see whether you really understand what all this means. Okay, so here's a second proof. Okay, and this is a much better proof. So now a proof, so I'm going to write this algebraically, the proof of Arrow, 1951, and DeBrew, 1951, separately. Okay, so this is called the fundamental theorem of economics, first welfare theorem of economics. Okay, so all this pictorial stuff makes so many assumptions. You know, there are only 2 kinds of traders, there are only 2 goods, they're somehow never, they're consuming only on the boundaries. I mean, they're never consuming on the boundaries. It's always in this, just so many special assumptions, and everything's 2 by 2, or it's just special case. So let's give a much more general proof of this theorem. So here we've got 2 goods won't play any role. There could be any number of goods. There are 2 goods only here, but there are many traders, lots and lots of traders. So what's the proof that X hat, Y hat couldn't Pareto dominate it? So suppose that we've got this is equal to summation X hat I, and this is equal to summation Y hat I. Okay, so we've got another allocation which is feasible. So could it be that this other feasible allocations of X hats and Y hats, could that make everybody better off? Could that make each I better off than Xi, Yi? And this proof is so short and so beautiful, so elegant, and so convincing that it's mesmerized people now for over 50 years, and it prevents them from seeing that there could be even more general situations where things aren't so great. So what is the proof? It's 2 lines. If X hat, Y hat is really better for I, then I claim, line 1, Wi of X hat I, Y hat I. Okay, so this is line 0. This is just repeating what's the case. Wi of X hat I, Y hat I greater than Wi Xi, Yi. Okay, that's for all I. That's the claim. Could this happen? That you've got a feasible X hat I, Y hat I, and it makes everybody better off than Xi, Yi. Okay, could this happen? The answer is no. Line 1 is, if that were true, then it would have to be the case that Px times Xi hat plus Py times Y hat I had to be greater than Px times Eix plus Py times Eiy. Why is that? Because the budget set of Mr. I says he spends all his money on X and Y in his budget set and does the best he can. Okay, this solves Xi, Yi solves this problem. So if this thing really makes him better off than what he chose, it can't be that it was affordable. Otherwise, he would have bought this instead. Bought this instead. So it has to be that this for I, this bundle costs more than he can afford. That's why he didn't choose it. So this relies on agent rationality. Everybody, given his choices, he doesn't care about the rest of the world, but given his choices, everybody's doing the best thing he can. Okay, now, Schiller would say people make mistakes, they're crazy, they have no idea what they're doing, they're stupid, there's some guy tells them a story in the bar one night and they totally change their life around, they switch, so he'd say, well, this isn't true. All right, but anyway, I actually believe that people have more sense about deciding for themselves what's good for them than third parties do about deciding what's good for them. So I don't want to challenge this. So if you don't challenge this, you conclude that if something makes everybody better off, each person must have found this allocation unaffordable. Otherwise, he would have chosen it. Over I of Eiy. So all I did was that's true for every single person I, so I could add this inequality for I plus this inequality for j plus this inequality for all the people, and then I use the distributive law to take the sum inside, and I have this. Okay, but that is impossible, and that's the end of the proof, because the sum of this x hat I is equal to this sum. That was what we had supposed. You're just rearranging all the goods that are really there. And this sum is the same as this sum. So therefore, since the new allocation just rearranges the endowment differently from the equilibrium and rearranges the x's maybe differently from the equilibrium, it has to be that actually this thing on the left is equal to this thing on the right. It's identical to it, so it can't be greater. And that's the contradiction. That's the end of the proof. So it's two lines to prove what, Adam Smith spent 400 pages arguing that the free market is a good thing. Okay, so this is the basis for the idea that we shouldn't regulate, we shouldn't regulate, we shouldn't regulate. Sounds pretty convincing. So any questions about this? Anything you'd like to say? Are you convinced by this? Okay, so what are some reasons you don't believe this? I mean, some obvious reasons. Yes?
Well, even if this proof makes sense, a lot of regulation policies have to do with changing the prices of things anyway. So we're not necessarily dealing with them at market prices they would be in the first place.
No, but that's, so you, okay, so it's a good, so that, I'm glad you asked that question because it betrays a misunderstanding. So I'm glad you asked that question. So suppose that someone came in, given these assumptions that we've made, okay, so this theorem is correct given the assumptions. Now, he made a standard, okay, so there's a little bit mistake in the reasoning he made. I'm going to repeat his question, change it a little bit, so maybe he'll deny this is what he was saying. But I believe what he just said is what really happens in a lot of regulation is they come in and they change the prices. They tax a good, they prevent people from trading so much so the price changes, they subsidize something. Something happens so that you get different prices, and of course at those different prices you get a different allocation. And then he said, that's all true so far, and then he said because they're at different prices, you know, you can't compare the original equilibrium allocation to the new equilibrium allocation. Well, that's where he shortchanged this proof. This proof says however you get to a new allocation, x hat I, y hat I, maybe it's because the government has intervened and changed all the prices and done a bunch of other stuff. But in the end, after all that intervention, the government is going to get you to a new allocation, x hat I, y hat I, and that new allocation can't be better than the original one. Okay, so that's the force of the argument. No matter what the government does, it's going to, in the end, the upshot is a new allocation, x hat I, y hat I. We don't have to think about how it got there. That's where it got. And according to this argument, it can't be better. So the argument is correct and elegant. There must be something missing to the argument, some assumption you don't really believe if you doubt the argument. Yes?
Well, what if you want an allocation that's better for one party, even at the expense of the other party?
What if you want an allocation?
It's socially desirable to have an allocation that's better for one party, even if that comes at the expense of another party.
Okay, so one argument you could say is that, all right, it may be in the equilibrium that A, okay, so who's better off here? You notice that this equilibrium, A ends up with more of everything than B does. Okay, so you could say this equilibrium is not very socially desirable because A ends up with more of everything than B does, or at least as much of everything as B does, and that seems unjust and unfair, and so we don't like the allocation, and so maybe we should move something from A to B. So that's an argument on the basis of justice. It says we can find juster allocations that are somehow socially more desirable. But this argument of Pareto efficiency is about efficiency. Okay, maybe you could, you could hurt A to help B because that's, serves your desire for fairness. But that doesn't say anything about how efficient the allocation is. It's still true that the original allocation was efficient in the sense you couldn't make anyone better off. So the economists would say, in order to hurt A and help B, what you should do is take some of A's endowment away from him and give it to her, and then let them trade to a new competitive equilibrium where she began with more than him. And so the just thing to do is to rearrange the resources at the beginning and still let people trade to a final allocation. Okay, so that's an argument from fairness, but it doesn't interfere, it doesn't contradict the economic argument that fair or unfair, it's still efficient. We've done as well as we could, making everyone as happy as we can. Maybe we can hurt someone and help someone else, but we can't help everyone at the same time. Whereas most regulation, the argument in favor of regulation is you're helping everybody by regulating. And this says you can't ever do that. So what's missing? What's some of the assumptions? This should be an elementary question for you. Yes?
Is it violating one of those three assumptions that we just quoted? The market theory?
No, it's got all those assumptions. So there's something about the model that's too narrow, and this should be easy, and you're going to tell me obvious things where it's too narrow, so I'm going to just say where we're going. You're supposed to be telling me now obvious ways this is too narrow. I'm going to say you're right, you're right, you're right, but finance is different. We don't have to worry about those problems, supposedly. So go ahead, back there, you. Okay, so one critical shortcoming of this argument is that they're externalities. Suppose that X is cigarettes, and A, buying and smoking more cigarettes makes B sick. Okay, so that's not part of this. Why is that not part of this? Because B's utility depends only on what B's consuming, not what A's doing. Okay, so there's no place in this model. It's too narrow to include externalities, so it doesn't capture the fact that A might be making, he by smoking might make her sick by smoking so many cigarettes, and that's not in here. And if you put the idea that utility, B's utility, her utility might depend on what he's doing and not what she's doing, the theorem won't be true. So there's a reason to tax pollution and to tax cigarettes and all those things because of externalities. Okay, so that's a fundamental problem. Yes?
We're also assuming that all of our indifference curves are going in the same shape.
Well, we're assuming diminishing margin utility, but they're different. Each person has a different indifference curve. So yes, we assume that they're all curved away from the origin, so we assume diminishing margin utility. But I think, that I'm almost prepared to believe, diminishing margin utility. It's not literally true, like 2 tickets are better than, moving from 1 ticket to 2 tickets may be a huge gain in utility because now you can bring your friend along, and going to a third ticket, going from getting 1 ticket might not be worth much because you don't want to go alone. Getting the second one may add a huge amount of utility. That's an increasing margin utility. But eventually, after you've got enough tickets, it's going to be diminishing margin utility. So I believe on the whole that diminishing margin utility is not such a bad assumption, but this clearly relies on that. So you're right, but I don't think that's the critical problem. What else is there? Yes?
Credit market.
What?
Credit.
Okay, credit markets. All right, now we're starting to talk a little bit about finance. So just hold that thought for 1 second. Anything else you can think of besides externalities that's terrible for, okay, so, all right, so let me transition this way. So, of course people noticed externalities. Another kind of regulation is perfect competition. We assumed everyone took the prices as given. There was no monopolist, setting the price and refusing to bargain with people and stuff like that. So regulation could come about in order to enforce the competitive equilibrium to allow for perfect competition. So we assume that already. That's one place for regulation. And a second place is because of these externalities. So for 50 to 100 years, everybody has accepted those 2 arguments. Clearly, there's a place for regulating free markets, ensuring free markets, and stopping trusts and monopolies, and for stopping externalities. But then people said, finance, okay, is different. As long as, there aren't any externalities. You're just trading stocks and bonds. There's no pollution. Nobody's going to get sick because someone else has a stock or a bond. Some people might be jealous, but we're not really going to take that into account. We don't want to honor those kinds of feelings of jealousy. So the argument seemed to be when you get to finance, you don't have to worry about externalities. And yes, you have to worry about perfect competition. But once you've got perfect competition, that's the end of the story. So the rest of the course now is going to be, if you forget about externalities, okay, because you forget about pollution, because, we're trading pieces of paper. They're not polluting anything. Why shouldn't the financial markets be efficient? Why doesn't this argument apply to the financial markets? And one of the critical financial markets is the credit market. So can you understand the credit market on just these terms and therefore argue that the market's efficient? So we're going to spend a large part of the course talking about that. So unless you had some particular point to raise now, I'm going to just use your comment as a good introduction to the next part of the course. Okay, so far there's nothing that seems to directly involve finance in what we've been talking about. So where does the finance come in? So Irving Fisher was the person who created the first really general equilibrium model of finance. So he was a Yale undergraduate. He, was a superstar Yale undergraduate, and he invented. Anyway, he graduated first in his class from Yale. He decided that he was a math major. He decided that he wanted to build a financial equilibrium model. There were no economists there at his time. We're talking in the late 1800s, and so he went to Gibbs, the famous physicist, maybe one of America's most famous physicists at the time, and said, "Can you advise an economics PhD?" And Gibbs said, "Well, if it's mathematical enough and has a model and something, yes, I can do it." And so Fisher's PhD dissertation was basically reinventing this general equilibrium model that I've just described, and then making a machine to calculate equilibrium with water and pumps and water seeking its own level and solving for equilibrium. And we had this machine up until the 1970s in the Coles Foundation when it got stolen. And some engineer named Srinivasan, about 10 years ago, was ready to rebuild the machine because we have the dissertation where it explains very carefully how Fisher built his machine, and he was going to rebuild it. And then he was offered El Baradai's job. El Baradai is the guy, the nuclear inspector who, goes to Iraq and says they're building nuclear stuff or not building this. Anyway, so he was offered that job, and so he left Yale and then decided not to take the job after all. So he still got El Baradai in the job. But anyway, he left Yale, and so we never got the machine built. He was a great guy. And anyway, so Fisher, after writing his dissertation, stayed at Yale as an assistant professor and he got tenure. He became the most famous economist probably in the country for a while. He invented finance, as I'm about to tell you. And he, in a way, this model of finance I'm about to present, which was the, in retrospect, clearly the most interesting model of finance of its time. And he was a financial economist, but he was famous for, he also was an entrepreneur. So you'll see later that he started his own company. It was a proto-computer company called Remington, and he managed to make $10 million for his company in the early 1900s. And he was a friend of Roosevelt's, and he kept advising Roosevelt during the Depression to print more money. He said, print more money, print more money, print more money. And the Yale Library has all these letters he sent to Roosevelt. And it also has Roosevelt's responses, where you can tell that Roosevelt is paying no attention to him. But Fisher's ego seemed to be so big that he just, Roosevelt says, I'm very glad that the good professor has made such worthy recommendations and will certainly take them seriously. And then Fisher writes back and says, I'm glad you're going to follow what I suggested. And so anyway, Fisher, convinced that the economy was going to turn around, poured all his money into this computer company, Remington. The company in the great stock market crash nearly went bankrupt and was leveraged. So he had to go to his wife, who was very wealthy, and borrow her money, and they lost that money. Then he went to her parents and borrowed all their money and lost that money. And finally, he'd lost everything of his own money, his wife's money, and his wife's parents' money. And they were about to take his house from him, foreclose on his house. And so Yale was forced to buy his house for him so he could continue to teach. And so he set a bad precedent for economists at Yale, because whenever any economist at Yale has financial advice to give, someone always quotes Irving Fisher's 1929 line that the economy had reached a permanently high plateau. And so, but anyway, despite all that, he still, his theories are well worth studying. He was famous for a few other things. He's a little bit, Schiller is clearly trying to imitate Fisher. Fisher wrote a huge number of books, 50 books about everything. So he got tuberculosis, and he survived, and he wrote a series of books on good living and good health and how to combat tuberculosis. So he said you had to exercise, you had to get fresh air, and these were huge bestsellers. And then he said that drinking was a terrible thing. So he did an experiment in class where he would have his students do push-ups. Then he'd give them all a martini. Then he'd count how many push-ups they could do. And then he'd give them a second martini and count how many push-ups they could do. And he found that there was a 10% reduction for each martini. And so he said that prohibition, since the average business person had 2 drinks at lunch, the prohibition would increase output by 20%. And so he's one of he was one of the leading proponents of prohibition. So after the stock market crash, he helped form the Coles Foundation. So Coles, who was a Yale undergraduate, had run a very famous macro forecasting company in the 1920s. And in 1929, the stock market crashed, and there were a whole series of these. They said newsletters, same kind of stuff they do now. He, unlike all the others, after the fact, realized that he hadn't anticipated anything about the crash, much like nobody anticipated it now. And he was so embarrassed, he went and collected not only his old recommendations himself, but all his competitors. And so he published a famous paper in which he argued that economists had no idea what they were talking about, the fact that they were frauds. And so he went to his old economist, Irving Fisher at Yale, and said, look, I just believe that economics without mathematics has no meaning. I want to start a mathematical wing of economics, and I've got a lot of money. His family owned the Chicago Tribune and the Seattle Times and a whole bunch of other newspapers, and there was a famous, fashion models in the family, Fleur Coles and stuff like that. So anyway, so with Cole's money, Fisher started the Econometric Society, which is the most famous mathematical society in economics, Econometrica, which is the most famous journal in economics, and the Coles Foundation, which they started off in Colorado Springs because Fisher said, oh, the weather's so good there, everyone will want to go there, and it's good for them. So nobody would go there, so they had to move it to Chicago, where the Tribune was. And it was in Chicago from 1930 to 1955. And then in 1955, it moved to Yale. And since then, the Coles Foundation has been at Yale, and you'll hear a lot more about it later. But anyway, so Coles, with that background, he set out to figure out how to turn economics. In fact, he invented economics, this model of equilibrium, to study finance. But so far, we don't have any finance in the model. So how can you put it in? Well, what is missing? What do I need to put in the model in order to turn it into finance? What would you say is missing? How would you turn this into finance? What are the key things? Yes?
Need some element of time.
Okay, so the first thing, so of course you may have read ahead in the notes, but that's a brilliant insight, if it's yours. You need you need time in the model. So far we just had, apples and oranges or something being traded. So the first thing, as Fisher said, you need to put time in the model. What else is critically missing in this model? One other thing, the major other thing, yeah. What? Okay, well, that's good. There's risk. That's missing entirely. So Fisher actually couldn't figure out how to put that in the model, but we're gonna get to that. So what else did Fisher? What else? Okay, that's very good. What else is missing? Yep. Okay. Wow. Okay. So time. Fisher, you'll see, had something to say about time and impatience, that people always care more about the present than the future. But what other fundamental thing about, what is the finance all about? When you think about finance, what do you think about? Yes?
Savings and credit rates.
Okay, so you think about credit, as she said. Credit, interest rates. Okay, and what else? Return, okay, that's quite related to that. So all this has to go in the model, but what fundamental object, when you think, the first thing you think about finance, what do you think of? Yes? Money. Okay, so that's not what I had in mind, but I'm glad you think about money. That's what he's right, that is what most people think about. So money. So in this course, we're not going to provide a theory of money. So Fisher did provide his theory of money, and that's what he was talking to Roosevelt about all the time, but we're not going to. So we're going to talk about inflation and stuff like that, but not a theory. We're not going to explain where the inflation comes from. So inflation is going to be very important, but we're not going to talk about a theory of money. So what else is missing? Something really basic, though. Yes? Okay, so there are no banks and things like that, institutions. Okay, and still something. Come on, what's the... What? Loaning funds. Well, somebody said credit. That's sort of loaning funds and interest rates and collateral. That's something. That's good. Now I'm going to add that. Thank you. What a brilliant idea. And what else? What basic thing? Come on. Yes. Wealth. Okay, that's in the model. Where's wealth? It's already there. So when you take your endowment and you multiply it by the prices in your budget set, that's your wealth. So wealth is already, we've got wealth.
Capital.
Capital. Okay, so capital, and let's say, and what is capital? What do you mean by capital? If it's money, I already told you that's not quite going to be there. So contract, well, okay, so we're getting there. Contract. Assets. Okay, so assets. That's the main thing. So I'm going to write it over here. Assets. Okay, after all, the stock market is about, the finance is a lot about the stock market, bond markets, mortgage markets. Those are all assets that you buy that pay money, pay dividends later. So assets are things that pay dividends at a later time. That's the critical thing that's missing. And when we talk about finance, we want to know, what should the value of the stock market be? How much should a mortgage be worth? Okay, so those are the things we have to add. Now, how are we going to add them? It sounds like you might have to just totally redo the theory and start from scratch and do something totally different. How horrible that would be. It would mean I also wasted 3 lectures. So Fisher said, you don't really have to change very much at all. So he said, number 1, time. How do you put time in the model? Simply think of y as the same good as x, but 1 period later. So Fisher said, time isn't such a big deal. We've already got 2 goods. These crazy marginalists before me, they had good x, which was interesting, and this very boring good y. And so, it's not so clear how you can have time and everything in the model. But I've already got 2 interesting goods, x and y. They're both, entering on the same, with the same symmetric properties. Neither one of them seems more interesting or more important than the other one. So in fact, maybe they're the same good. It's just x and y is the same good. It's one comes 1 period later. Now, next class, we're going to talk about you're not going to value them the same amount. The utility for x and y won't be the same. So here, A obviously thinks more of x than he does of y. And by the way, B, she also thinks more of x than she does about y. So why is that? Well, if y is the same as x, but a year later, people are impatient. So the reason why A might like x better than y and B also is not because they're different goods, but because they're impatient. So we're going to come to that later. So we can have the idea that there are 2 different time periods in the economy simply by a change of notation and not introducing anything new at all. Well, what about assets? How can you put, so I'm going to come back to that in the next class. What about assets? How can you introduce assets into the economy? Well, Fisher says, what is the essence of an asset? The essence of an asset is that it's something you hold today because later it's going to deliver you money or goods or something. And we're not going to talk about money, so we're imagining these are all real assets. So they're going to deliver goods in the future. So asset, the definition of an asset is an asset. Remember, we have to make it mathematical. So the whole Fisher started the society to make economics mathematical. So an asset is literally something that delivers goods in the future. So an asset is defined by its payoffs. dx and dy. So we could call that asset alpha. An asset alpha is defined by its payoffs, dx and dy. So it's going to pay a certain amount of x and a certain amount of y. That's all there is. Now, we're going to ask, do people actually know what the payoff of y is going to be? If y is in the future, that means it hasn't happened yet. Do we really know what y is going to be? And so Fisher, so we have to, and so, maybe we know less about one asset, more about another asset. So maybe one asset's riskier than another asset. So someone said risk. Obviously, that's going to be a very fundamental question. But before we come to risk, if we don't have any risk yet, because Fisher didn't know how to put it in, and we're going to start with his model where there's no risk, okay, then if there's just today and tomorrow, and everybody's rational, everybody, since there's no uncertainty, everybody must be able to anticipate exactly what the dividend is going to be. So the asset is no different from what its dividend is going to be. Maybe it's paying something today and also it's going to pay something tomorrow. So assets are defined by their dividends, nothing more than that. So the model now becomes a model where we have the WI, and then we have WI, and then we have the goods as before, the endowments of the goods, but we've added a new thing, which is we've added the assets, d alpha x and d alpha y, So the alpha is over all the assets, and we have to add everybody's ownership of the assets to begin with. So we have to have theta, I'm going to call it theta bar alpha, theta bar I alpha. So how much of asset alpha does I own? So that's the economy that we're going to start with. Okay, so we've made the model we've made the model a bit more complicated. We started where we did before with utilities and endowments of goods. Now we're adding assets which pay off more goods, and of course people begin owning trees and stuff like that. So a tree is an asset. It's going to pay apples later on. And various different people own various different trees. So we've got, to the old economy, we add something new. And now Fisher's ingenious insight was that if you think about this, which we will for a little while, you'll be able to discover that you can simplify this economy back down to the economy we began with. So you can start talking about assets and interest and all kinds of other things using the same analysis as before. So with my last thought here, what does interest have to do with px over py? Suppose they're both, what is px over py? Suppose they're both apples. So x is an apple today, y is an apple next year. What is px over py? It says how much an apple is worth today relative to how much an apple is worth tomorrow. So this is going to turn out to be 1 plus the real interest rate, Fisher would call it. Okay, because if px is more than py, let's say px is 20% more than py, what it means is by giving up 1 apple today, you can get 1.2 apples tomorrow. That's just what happens when you put money in the bank. You give up something today, you get exactly the same thing back next period, but more of it. So you see, just by having time and the prices like we had before, you're going to see very quickly how interest, assets, everything is going to start coming into play very quickly. So I didn't put the problem set on the web yet because I wasn't sure how far we'll get, but I'll put it on in a couple hours, and we'll start again on Thursday.